Okay, this is Jordan. Welcome to assignment 2, part 1. We're going to work on naming number 15, the compound that I cherry picked. So to start, in the orange, we have a 6-carbon chain, which is linear and a hexane. It's not a cyclo. So we know that. Then if we start at the first carbon, I'm going to number left to right because I want my functional groups to have the lowest numbers possible. We have in blue a nitro functional group, NO2. And then on the second carbon, we have a hydroxyl or alcohol. And then on carbon 5, we have 2 fluorine atoms, so difluoro. So how do we put this all together? So I took a look at the functional group chart we made in class, and I didn't see nitros. So I had to look, had to do a bit of searching online. And I found, with priority, that nitros are down here. So in terms of functional group priority, as a rule of thumb, the higher the oxidation state of the central atom, the higher the priority of the functional group. So in this case, the nitro is connected by the nitrogen atom, so it's not directly connected to the central carbon, but the hydroxyl is connected. And so we're going to, from a priority standpoint, this functional chart helps indicate that nitros have the lowest priority, lower than halogens, lower than ether, and way up here is carboxylic acid. So we got an alcohol, we got our halide, and so I'm going to say the parent chain suffix is an alcohol. So I'm going to start by writing hex, and now our alcohol is on the second carbon. So 2 dash all, which we learned in class. Now we need to prioritize the functional groups alphabetically. So we're going to move on to focus on the fluorine atom, fluorine atoms plural, and the nitro group. So it's 1 nitro as the prefix, and it's 5 difluoro, but F alphabetically comes before N, so it's going to be 5, 5, because there's two of them, difluoro. Then we tackle our nitro group, 1 dash nitro. Now, before I'll pause here, now because the nitro functional group, there should be no dash before the hexane, so it would be 1 dash nitro, and we got to close the space, hexane. So I'll rewrite that to make it nice and clean. It'll be 5 difluoro dash 1 nitro, notice lowercase, hexane 2 all. So this beautiful molecule, or compound rather, is 5,5 difluoro 1 nitrohexane 2 all. Welcome to the second part of assignment 2, where we're going from the name of the molecule for the one I cherry picked, number 15, this is Jordan, to the condensed, expanded, and line/skeleton structures. So I picked 2,2-cyclopentyl 3-methyl butanoic acid. So that's a mouthful, but it breaks down to a carboxylic acid on the end with OIC acid. Butan implies a linear alkane that has 4 carbons. There's a methyl group on the third carbon. Now we know because carboxylic acid, we're going to have a 4-carbon chain, and the first carbon will have the carboxylic acid on it. So this will be carbon 1, then we'll draw out our carbon chain, and on carbon 3, we're going to have a methyl group, and then we have this crazy structure over here, 2,2, so we have 2 functional groups that are identical, cyclopentyl, so 5-carbon cyclic alkanes that look like a house. So if we go over to our expanded, so starting at carbon 1, we got our carboxylic acid with the carbonyl group and the hydroxyl group. Then we go to carbon 2. And pink is the 4-carbon chain for the bute, and we got our houses, as I call them, so cyclopentyl. So there are no hydrogens with the exception of the one in the OH. So 1, 2, 3, 4 bonds, so double bond here, right? So that's four bonds for this carbon. For this carbon, we got 1, 2, 3, 4 bonds. So if we go over to the cyclopentyl functional groups, so this first carbon will have 1 hydrogen on it, it'll be a CH. The remaining carbons in the cyclopentyl functional group will be CH2s, 1, 2, 3, 4. Same thing here, CH, 1, 2, 3, 4, CH2s. Then if we go to our third carbon, as we know over here in orange, it's a methyl. So this carbon has 1 bond, 2 bonds, 1 bond to the methyl, so that's 3, so we need a hydrogen. So this is a CH. And then finally, the fourth carbon is a CH3, 1, 2, 3, 4, with the most hydrogens. Moving on to our condensed form. So I started it over here, but I drew it more neatly over here. So here's our main chain in our parent chain in pink. So we got carbon 4, carbon 3, carbon 2, and carbon 1 in pink. So starting over here, really, so we got the carboxylic acid with the C double bonded to the O, OH, and I use blue to show that pink, that it's part of the main chain, but it's part of the carboxylic acid group. Then we have a C, which the cyclopentals are connected to in the parent chain. So the cyclopental groups have 4 CH2s, as mentioned, CH2, 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 and a CH, and there are 2 of them, so there's a 2. Then there's the third carbon, which is a CH with 1 hydrogen, connected to a methyl group up here, so it's CH3 in brackets. And finally, fourth carbon, CH3. So that is the condensed structure. Moving on to my lovely, I'm not an artist by any means, our lovely skeleton or line structure. So initially, I drew my my line structure counting this way, left to right, but we're actually going to count in blue from right to left. So here's carbon 1, here's carbon 2, here's carbon 3, here's carbon 4. So on carbon 1, in blue here, that's the 1, we got our carbonyl and our hydroxyl for our carboxylic acid. Then for carbon 1, carbon 2, we got our 2 houses for our 2,2 cyclopental, so they're denoted in green. And then on carbon number 3, we've got our methyl group in orange coming off the third carbon. And then finally, we got our fourth carbon, which is CH3, as mentioned, to finish it off. So shorten here, moving on to discuss the properties of our second compound, number 15 that I cherry picked, 2,2-cyclopentyl 3-methyl-butanoic acid. All right, so overall, this is the more reactive compound compared to 5,5-difluoro-1-nitro-hexane 2-ol. The reason is there's an overall dipole to the molecule, despite it being predominantly hydrocarbons. Because of the carboxylic acid, there's a net dipole going this way. And now, due to the size of the molecule being fairly large from a reactivity standpoint overall, both of these molecules are reasonably large. It makes it less reactive than smaller molecules. So for example, comparing 2,2-cyclopentyl 3-methyl-butanoic acid to, say, hydrochloric acid being smaller helps its reactivity. Now moving on to the molecular geometry. So carbons 2, 3, and 4 are tetrahedral, AX4, with a bond angle of approximately 109.5 degrees. But when we get to carbon 1, there's a trigonal planar geometry because of the carbonyl group, and that's approximately 120 degrees. Overall, there is a net dipole to the compound, as I said, negative of this going this way. It's soluble in polar substances like water and alcohol. There's hydrogen bonding due to the carboxyl group, and as mentioned, there's a net dipole because of the carboxylic acid. And there are some London dispersion forces, but it's not the dominant intermolecular force. Now we're going to talk about the properties of compound number 1 in assignment number 2, number 15 that I cherry picked. This is Jordan here. So overall reactivity, this is a somewhat reactive molecule overall. It's reactive at the functional group levels, but due to the fact that the overall compound is fairly nonpolar, that limits its reactivity. We have fluorine atoms, which we know are the most electronegative atoms. So those will be highly electronegative and reactive. We also have a hydroxyl group or an alcohol group that will change the properties of everything and will be fairly reactive. The nitro group is not very reactive. So overall, the compound is somewhat reactive. Moving on to molecular geometry. So we are going to have tetrahedral and which is sp3 hybridized throughout. So here we got bonded to 2 hydrogen atoms and then bonded to 1 functional group here and then another carbon. Here we've got 1, 2 bonded to a hydrogen, bonded to the functional group. So we know tetrahedral is not polar, and so it's fairly not polar overall. When it comes to bond angle, we know AX4, and therefore it's approximately 109.5 degrees. From a polarity standpoint, overall the molecule is fairly nonpolar, but regionally, as mentioned, with the fluorine, with the hydroxyl, it's got polar regions. There is no net dipole to the molecule overall, and it is it's soluble in polar substances like water and alcohol. From an intermolecular force standpoint, the hydrogen bonding with the OH group is the dominant molecular force. There's a weak dipole in the nitro group, and there's a stronger polar covalent dipole occurring with the fluorine atoms because of how electronegative fluorine is compared to carbon. And there are some London dispersion forces, but it's not the dominant intermolecular force for this molecule.